Welcome back to Tungal College online classes. Hello students, how are you all? In last class you learned valency bond theory and overlapping of atomic orbitals and types of overlapping. But today's topic is types of covalent bonds based on type of overlapping. Based on type of overlapping, covalent bonds are classified into mainly two types. One is a sigma bond, another one is a pi bond. Now let us write them. The first one is a sigma bond. Sigma bond, and the second one is a pi bond. The second one is pi bond. Now let us discuss one by one in detail. The first one is a sigma bond. The sigma bond is formed by the end-to-end overlapping of atomic orbitals. Now what is the meaning of this statement? Let us understand by taking an example. I am taking this is a 1 p orbital. This is a 1 p orbital. I am taking another p orbital here. This is another p orbital. Another p orbital. This is the end part of this p orbital. This is end part of p orbital, and this is end part of this p orbital. These are the end parts of p orbital, and this part is a bottom part. This is a side part. This is the side part of p orbital, and these are the side parts of p orbital. But in this case, sigma bond formation, end part of p orbital overlap with the end part of p orbital. End part overlap with the end part. Now what we'll get is let us see. Right, like this we'll get. So this is the end-to-end overlapping. End-to-end overlapping of p orbital. End-to-end overlapping form the sigma bond. The sigma bond is formed by end-to-end overlapping of atomic orbitals. Now we can take one more example. I am taking this is the p orbital, and I am taking s orbital. This is s orbital. S orbital. The end part of the p orbital overlap with s orbital. Then what is the resulting thing is we will get like this. Right. This is also a end part. This is also a end on end overlapping. This type of overlapping leads in the formation of a sigma bond. How do we define? How do we write the statement regarding sigma bond? The sigma bond is formed by end to end overlapping of atomic orbital. Write the same sentence. The sigma bond is formed. The sigma bond is formed by end to end overlapping. End to end overlapping of atomic orbitals. End to end overlapping of atomic orbitals. This is the information regarding the sigma bond. Now coming to the pi bond. The pi bond is formed by the sidewise overlapping of atomic orbitals. I will show an example. So this is a p orbital. This is a p orbital, and I am taking another p orbital. This is another p orbital. These two p orbital. This is side part of p orbital, and this is a side part of p orbital. For this case, this is the side part, this is the side part. Side part overlap with the side part of p orbital, not end part. This is the end part, this is the end, but we are taking is side parts. So side part, this one is the side part. This is the side part of this p orbital, and this is the side part of this p orbital for these two loops. Here is this is the side part, and this is the side part. Side part overlap with the side part. The resulting bond is a pi bond. So the pi bond is formed by the sidewise overlapping of atomic orbitals. Now what we will get is like this. This is sidewise overlapping of atomic orbitals. Now how to write the statement regarding the pi bond? The pi bond is formed by sidewise overlapping of atomic orbitals. Write the same sentence. The pi bond is formed by sidewise overlapping of atomic orbitals. Sidewise overlapping of atomic orbitals. For PEC point of view, this what is the sigma bond, what is the pi bond is very, very important. So this is the sigma bond and pi bond. And simply sigma bond is formed by end to end overlapping of atomic orbitals. Pi bond is formed by sidewise overlapping of atomic orbitals. Next topic is difference between the sigma bond and pi bond. So I am taking sigma bond one side, pi bond I am taking another side. First I am taking sigma bond. Sigma bond one side, I am taking pi bond here. Now let us see the difference between the sigma bond and pi bond. So point number 1 regarding the sigma bond. Already we discussed this point. Sigma bond is formed by the end to end overlapping of atomic orbitals, and pi bond is formed by the point regarding the pi bond. Pi bond is formed by the sidewise overlapping of atomic orbital. This is end to end, this is sidewise. So this is one difference. The first difference, it is formed by end to end overlapping of atomic orbitals. It is formed by end to end overlapping of atomic orbitals. Now the difference for this case is what we have tried. It is formed by sidewise overlapping of atomic orbitals. Sidewise overlapping of atomic orbitals. This is the first difference. The second difference is sigma bond is a strong bond. Then opposite is it is a weak bond. So let us write the sentence. It is a strong bond. It is a strong bond. And opposite we have to take strong bond opposite. This is weak bond. It is a weak bond. It is a weak bond. Now one question is arises. Why the sigma bond is strong bond? Why the pi bond is weak bond? Let us take an example. I am taking this is one p orbital. This is one p orbital. And this p orbital overlap with imagine another p orbital like this. This is the overlap. So this end on end overlapping. This is the end part is overlapped with this is the end part. End on end overlapping. What the bond is? Sigma bond. This is a sigma bond. So the sigma bond is first bond formed between any two atoms. So this is the sigma bond, and I am taking another p orbitals. This is another p orbital, and this is another p orbital. Clear? Then this is the side part of p orbital, this is the side part of p orbital. Then the bond formed between the side parts, this is a pi bond. Here is we get pi bond. So bottom is also pi bond. So pi bond is formed by sidewise overlapping. This is end on end overlapping. Now the point is already this is imagine one lobe of p orbital. This overlapping is maximum extent. Overlapping will be maximum extent, and this p imagine these fingers considered as a considered as orbitals. This cannot overlap maximum extent because they are far away from each other. These two far away from each other, the overlapping is not maximum extent, but here the overlapping will be maximum extent. I'm placing one more. This is one p orbital, this is p orbital. When they came to end by end, overlapping will be maximum. This case I'm talking, this case overlapping will be maximum because they are end to end. After formation of sigma bond, here these two lobes are far away from each other. The overlapping is not maximum extent. Because of the overlap, these orbitals are far away from each other. They cannot overlap maximum extent. Overlapping will be weak. So overlapping is not maximum in a sense, that will be weak extent. Weak. So because of the weak overlapping or overlapping is not maximum extent, this bond is a weak bond. So this is a sigma bond is a strong bond, and sigma bond is a strong bond, pi bond is a weak bond. What is the statement? Why? The reason is the sigma bond is formed by maximum extent of overlapping, maximum extent of overlapping. And pi bond, in the case of pi bond case, the overlapping is not maximum extent. Overlapping is maximum extent here, overlapping is not maximum extent. This is the one difference. Difference number 3. Sigma bond electrons, referred as localized. The sigma bond electrons are referred as localized, and the pi bond electrons are referred as mobile electrons. Mobile electrons are free electrons. So what is this point is, these are the electrons in between these two bonds. Here is the electron is located. Between these sharing will be takes place. Here electrons located between these electrons between the nuclei of two atoms. So these are localized. But here is extent is overlapping is not maximum extent. So that those electrons present in these orbitals are referred as a free electrons are mobile electrons. So this is the third difference. And next difference is sigma bond can exist independently. Sigma bond can exist independently. It can exist independently, and pi bond exist along with pi bond can exist along with sigma bond. So this sentence meaning is first bond is formed between any two atoms is a sigma bond. First bond is a sigma bond because end to end overlapping. After the formation of sigma bond, then pi bond is get formed. So pi bond is formed after formation of a sigma bond. So that the first bond is a sigma bond, then pi bond is formed. So it can exist independently. Some molecules only contain sigma bonds. Some molecules have pi bonds. So the sigma bond can exist independently, but pi bond will be always formed along with pi bond is formed always along with the sigma bond. After formation of sigma bond, then pi bond will be formed. So that sigma bond can exist independently, and pi bond can exist along with the sigma bond. So these are the differences between the sigma bond and pi bond. Next topic is hybridization. It is proposed by the Pauling and it is a theoretical concept. So hybridization is defined as the intermixing of atomic orbitals of slightly different energies so as to redistribute their energies to produce a set of orbitals with equivalent energy or same energy is called as hybridization. So this is the definition of hybridization. Let us understand what is exact meaning of this definition by taking an example. So I am taking an example, s orbital. This is s orbital, and I am taking another one is p orbital. This is p orbital. One I took s orbital and this is p orbital. The intermixing of s orbital and p orbital will produce a new set of orbitals. This is sp hybridized orbital, this is another sp hybridized orbital. So we'll produce a new set of orbital. These orbitals are called as hybrid orbitals. So we are intermixing of s orbital and p r with slightly different energies to produce a new set of orbitals with equivalent energy. So this phenomenon is called as hybridization. I will take one general example for better understanding of this hybridization concept. Suppose I am taking rice. Rice imagines particle size we know very well. Then you can take the pulses, like you can take black gram. You know the size of the particle. Compare the size of the rice particles and black gram particle. Any pulses you can take. Compare the sizes. The sizes will be different already, you know very well. Understanding purpose I am telling for this concept. So the sizes of these particles are different. Now place them in a water overnight. Morning itself you grind them. So when you grinding in the sense you can make it a mixie. Then after making them, after grinding them, what you will get is a slurry. Look at at the particles in the slurry. Thus, in the slurry you will get particles is small in size. Initially, size of the rice as well, size of the particles of rice and black gram size of the black gram particles will be different. After mixing, you will getting a same sized particle. The same concept understanding purpose you can apply here. So instead of taking the size of the particle, you can take energies you should consider, not the size, consider energy. S orbital and p orbital, they have, imagine they have slightly different energies, like slightly different the sizes, they have slightly different energies. Clear? Then we have to intermix. How do you mixing rice particles and black gram particle pulses? How do you intermixing? Similarly, understanding purpose, we have to intermix them. If you intermix them, you will get a new set of orbitals. There you will getting a slurry small particles you are getting. Here you are getting a new set of orbitals with the same energy. How the same size particle you are getting there? Similarly, you are getting same size, same energy orbitals you will get. This phenomenon is called as hybridization. I am repeating, intermixing of atomic orbitals of slightly different energies so as to redistribute their energies to produce a new set of orbitals with equivalent energy or same energy is called as hybridization. I am repeating one more. Size of the rice and size of the black gram will be different initially. After intermixing, they will get to same sized particles. Here also, the energies of s orbital and energy of the p orbital is different. After intermixing, you will get same energy orbitals, orbitals with equivalent energy. This phenomenon is calling as hybridization. Now let us write the sentence what we explained. So the first one is the intermixing of atomic orbitals, with slightly different energies, so as to redistribute their energies, to produce a new set of orbitals with equivalent energy or same energy. Equal energy or same energy is called hybridization. And the new set of orbital formed with equivalent energy is called as a hybrid orbital. Write the sentence. The new set of orbitals formed, new set of orbitals with equivalent energy, or same energy is called hybrid orbitals. So this is the definition of hybridization and hybrid orbitals. Simple words. Initially, atomic orbitals are slightly different energies. We are mixing them. We are producing a new set of orbitals with the same energy. So different energy orbitals converting into same energy orbitals. This phenomenon is called as a hybridization. Now, this phenomenon is called hybridization. Now, there are different types of hybridizations. Types of hybridization. There are different types of hybridization. So the first one is sp hybridization. The second one is sp2 hybridization. The first one is sp hybridization, second one is sp2 hybridization, third one is sp3 hybridization, sp3 hybridization, and the fourth one is sp3d hybridization, sp3 hybridization, and the fifth one is sp3d2 hybridization. Fifth one is sp3d2 hybridization. These are the different types of hybridization. Now let us discuss one by one in detail. The first one is sp hybridization. In examination, you will get the questions like what is the hybridization, explain the hybridization of BeCl2 molecule, or they will give explain the hybridization of CH4 molecule, or they may give explain the hybridization of PCl5, NH3, and we have ethylene molecule, acetylene molecule, water molecule, etc. Many number of molecules is there. So what we have to do is we have to apply the hybridization concept to the molecules. Molecules are very, very important. Now let us discuss some examples of molecules by taking one by one with hybridization. So we will discuss hybridization by taking suitable examples. Among them, the first one is sp hybridization. So what is the sp hybridization? One s orbital intermixed with one p orbital, resulting in the formation of two sp hybrid orbitals. What is this statement meaning is, I am taking this is one s orbital, this is one s orbital, I took only one, and I am taking one p orbital, this is one p orbital, this is one p orbital, both are intermixed. After intermixing you will get two sp hybridized orbital. One s orbital intermixed with one p orbital, the resulting in the formation of two sp2 hybridized orbitals. Now another important point is how many number of pure atomic orbitals are intermixing, that many number of hybrid orbitals are formed. Here is how many intermixing. This is one s orbital, this is the second p orbital. Only two orbitals are intermixing, you will get two hybrid orbitals, sp hybrid orbitals. Suppose if three are intermixed, now example I am taking one s orbital intermixed with two p orbitals. This is one p orbital and this is another p orbital. This is one and these are the two p orbitals. Total number of orbitals are intermixing how many? Three are intermixing. If three are intermixing, you will get hybrid orbitals must be three. This is the first one, this is the second one, and this is the third one. So this is one sp2, this is another sp2, this is another sp2. So the point is how many number of pure atomic orbitals are intermixing, that many number of hybrid orbitals are you will get. This point you should never forget. Based on this only you will write the different molecules. Now another important point is continuation. One s orbital I am taking three p orbitals. This is the first one, this is the second one, and this is the third one. So simply one s orbital I took, three p orbitals I took. The total number how many I took? 4. Then 4 of pure atomic orbitals are intermixed. Then how many hybrid orbitals are we will get here? How many we can expect? 4. This is the first one, this is the second one, third one, this is the fourth one. So each one is, this is sp3, this is another sp3, and this is third, and this is the fourth one. Here is 4 is intermixed, 4 hybrid orbitals we got. 3 atomic orbitals are intermixed, 1s, 2p, we get 3 hybrid orbitals we got. 1 s orbital, 2 p orbitals, 3 sp2 hybrid orbitals. Coming to here, our topic. Here is 1 s orbital intermixed with 1 p orbital, leading the formation of 2 sp hybridized orbital. 2 sp hybridized orbitals. Write the same sentence. What is the sentence? It involves intermixing of 1 s orbital, intermixing of 1 s orbital and 1 p orbital. 1 s orbital and 1 p orbital, resulting in the formation of 2. How many we got? 1 s orbital, 1 p orbital we get. This is sp, this is sp. 2 sp hybrid orbitals, hybridized or hybrid orbitals. This is the first statement. And another one is how much percentage of S character and how much percentage of P character we have to find out. Imagine this is 100%, this two orbitals together is 100%. So we 100% we have to divide to the two orbitals are formed. How many? Yes, one S, one P will be there. Two orbitals is there. So 100 by 2 in the sense 50% is S character, 50% is P character. So the sp hybridization contains 50% S character and 50% P character. Next point. The sp hybrid orbitals contain 50% S character and 50% P character. 50% is S character, 50% is P character. And another important point is the bond angle between the two hybrid orbitals. The angle between two hybrid orbitals, this will be. This angle is both are will be taken as linear. The angle will be taken as 180 degrees. The angle between the hybrid orbitals is 180 degrees. Write the same sentence. The angle between sp hybrid orbitals is 180 degrees. The angle between sp to hybrid orbitals is 180 degrees. And another point is the molecules with sp hybridization has a linear shape. Any molecule with sp hybridization, they have linear shape. Write the same sentence. The molecules with sp hybridization. The molecules with sp hybridization is linear in shape. The molecule with sp hybridization is linear in shape. So this is the statements regarding the sp hybridization. What is the first point? Any hybridization will write mainly these 4 points. What is the first point for any hybridization? The first point is what is the hybridization? This hybridization is it involves the intermixing of one s orbital, one p orbital, resulting in the formation of two sp hybrid orbitals. This is the first point. And next one is what is the percentage of s character and p character? In this case, total will be taken as 100%. Only two orbitals is there. So one is 50%, s character is 50%, p character also 50%. And the third point is angle between the hybrid orbitals. Angle between these two are linear. The angle is 180 degrees. This is the third point. Fourth point is what is the shape of the molecules? The shape of the molecule, any molecule with sp hybridization, they have linear in shape. For any hybridization, you have to write these 4 points. Now let us take one example. And we should apply this hybridization concept to those molecule. I am taking example. I am taking BeCl2 molecule. Right, while hybridization concept is applying to this molecule, so we have to take 2 steps is there. The first one is a hybridization step. The first step is a hybridization step. And the second step we have is overlapping. The second step is overlapping step. The first step is hybridization step, and second step is overlapping step. Then coming to the first hybridization step. So while writing the hybridization step, first we can take the central atom beryllium, write it electronic configuration. So beryllium at the center, write its electronic configuration 4, and electron configuration is 1s2, 2s2, 2p0. So this is the first shell, these two are the second shell, p orbital, no electron is there, you can write. So only the valence shell orbitals involved in the hybridization. Valence shell orbitals only involved in the hybridization. Now this electron configuration we are taking as ground state. This is a ground state electronic configuration. Original state of electronic configuration, ground state of electronic configuration. Then we have to write the electronic configuration in the form of boxes. This is the 2 electrons is there, 1, 2. Here is p orbital, there is an electron 0. p orbital there is an electron, 0. No need to fill this orbital. Now, in excited state, one electron present in the 2s orbital will be jumped to the 2p orbital. So, we have to make it as 2 single electrons, because 2 chlorine atoms is there. We have to share with 2 chlorine atoms, 2 single electrons we have to make there. Then this electron will be jumped to here. When electron is jumped here, then we will get beryllium, and this is excited state. Excited state electron configuration. Excited electron configuration, this 1s2 remains same. This electron went here, then this will be 2s1, 2s1. The one electron came here, this will be 2p1, 2s1, 2p1. For this also you should write a orbital diagram. Listen carefully. Orbital boxes. Then here is the one electron, here is the another electron. Clear? Initially, the 2 electrons present in the s orbital only. This state we are calling a ground state. Whenever electrons is jumped to another orbital, we are writing it as excited state. This is excited, this is ground. Difference is electron will be jumped from 2s to 2p. As a result, 2p also has one electron. Initially it is 0. Clear this point. So 2s1, 2p1. How many orbitals we got? One s orbital we got, one p orbital is got. Then one s orbital intermix with this s orbital intermix with this p orbital, only one p orbital. This s orbital intermix with this p orbital leading to the formation of 2 sp hybridized orbitals. I said one s orbital intermix with one p orbital to form 2 sp hybridized. This s orbital intermixed with this p orbital. This p orbital, the leading to the formation of sp hybridized orbital. This is one sp and this is another sp hybridized orbitals are formed. Clear? Then this is a hybridization step. The first step is hybridization step. After completion of hybridization step, we have to go to the overlapping step. In overlapping, we have to take chlorine atoms. Clear? Hybridizations we did not consider chlorine atom. Don't confuse here. Here first I took the beryllium only. For the beryllium, first I write electronic configuration in a ground state. I took the orbital boxes. Right? Box electron fill in a boxes. Then one electron jumped here. Then I got this electron configuration. Why should I jump only one electron? The reason is 2 chlorines is there. It required to share the bond. 2 bonds we have to make one beryllium with one chlorine and beryllium with another chlorine. So 2 bonds we have to make. We require 2 single electrons. So that I jumped one electron here, I got 2 electrons. Then I mixed how many? I got one s orbital, one p orbital. These two intermixed, we got sp hybridized orbitals. Clear? This is the first step. Coming to the second step. Then in the second step, chlorine is there. Chlorine atomic numbers we have to take. Chlorine atomic number is 17. So this is 1s2, 2s2, 2p6, 3s2, 3p5. In only valence shell, this is the first shell, this is the second shell, this is the third shell. Valence shell only we have taken. So how many is there? 1, 2 electrons. This case 1, 2, 3, 4, 5. Only this is only one electron is there. Clear? And one more chlorine is there. To this chlorine also we have to take a same electronic configuration. 1s2, 2s2, 2p6, 3s2, 3p5. Isn't it? Then for this case also take the orbital diagram. 1, 2 orbital boxes. Only one electron will be there. This p orbital overlap with this p orbital overlap with this sp hybrid orbitals. So we can show how the overlapping is. I am writing this one here. I need some space so that this is one sp and this is another sp. Clear? Right? Overlapping we are doing. How to do overlapping is first I am taking these sp hybrid orbitals. This is from beryllium. This is from beryllium sp and this is sp from beryllium. 2 chlorines. This is one chlorine. This is from one chlorine. This p orbital from one chlorine and this p orbital from another chlorine. This is from one chlorine, this is from another chlorine, this is from beryllium. Center I am keeping beryllium. At the ends I am keeping chlorine p orbital. This p orbital labeling as like this. This has one p orbital. This I am labeling as 1 because we don't take this p orbital, this p orbital, because it has only one electron. This one, this p orbital, and this has only one electron. These two p orbitals we have to take. This p orbital I wrote here, this p orbital I wrote here, beryllium I wrote at the center. Then overlapping already you know very well. How do we do overlapping? Partial merging. This one we have to merge here, this one we have to merge here. Then make the overlapping like this. Clear? So this is a beryllium at the center. After overlapping beryllium at the center, between the beryllium and the chlorine one bond is formed. This overlapping leading to the formation of a bond. Between the beryllium and chlorine one bond is formed. This is a BeCl. Finally, how try to overlapping like this. Then angle. So BeCl, the angle is 180 degrees. The angle is 180 degrees. Another important point here is the shape of the molecule is linear. These points you have tried. You will get much understanding by taking some more examples. If you take the examples one by one, you will get much clarity of hybridization. So next class I will come out with another topic.